Hey students, welcome to Trigonometry 101. Well, actually it's Algebra 2B, but that's kind of what they usually call a class where you get the basics of something. They call it 101. And that's what we're going to get in this chapter. We're going to be getting the basics of trigonometry. So what is trigonometry? Well, let's take a look at a little video clip that will tell us a little bit about where you see trigonometry, and then we'll learn some of the basics in this lesson and in upcoming lessons. So let's go ahead and tune into the video now.
Why is trigonometry useful? Well, the short answer is because trigonometry can be applied to any topic that involves distances, angles, or vibrations. Sine, cosine, and tangent functions show up all over the place in science and engineering. Here are a few examples. Why is the sky blue? The sky's blueness can be explained by Rayleigh scattering. Light with shorter wavelengths gets scattered more. Here's the equation for Rayleigh scattering, and notice the cosine squared term. Another example is the discovery of the atomic nucleus. About 100 years ago, Ernest Rutherford bombarded gold foil with alpha particles to discover that protons were bunched together in atomic nuclei. Here's the cross-section for the nucleus that he discovered, and sure enough, sine to the fourth term in the denominator. Aero and astronautics make great use of trigonometry. A simpler example of this is when planes turn, they bank by an angle theta, and the radius of their turning is given by the following equation. Notice the tan theta in the denominator. Medical imaging is yet another example. Here's an MRI of a knee. MRI measures the spins of atomic nuclei in magnetic fields. Here are equations that describe how a spin rotates or precesses in a magnetic field. And there's plenty of trigonometry in that. How about navigation and GPS? When calculating the distance between nearby latitude and longitude coordinates, you can use the following equation, which of course contains the cosine of your current latitude. And then there's data compression. Here are two images of the Earth. The one on the left requires 6.5 megabytes of disk space, while the one on the right requires 10 times less space, only 400 kilobytes. One way to compress data is to use a Fourier transform, which is shown here, along with its cosine and sine terms. Quantum mechanics is littered with trigonometry. If you want to find electron positions or orbitals within atoms, some of which are displayed here, you would want to use spherical harmonics, which involve cosines. If you want to be an architect, you better know your trigonometry. Architecture is all about balancing forces and keeping structures stable. For example, if you want to build a suspension bridge, how do you calculate the shape of the wires that hold the bridge up? Well, you'd use trigonometry. From the dawn of time, trigonometry has been helpful in telling time, from sundials to pendulums to atomic clocks. Here's an equation for the position of a pendulum as a function of time, involving the cosine. Trigonometry also has its uses in biology. For example, if you're modeling protein folding using force fields, you'll want to calculate the torsional energy in bonds, trigonometrically. And our last example are 3D movies, which can make use of polarized light. If the left eye sees one polarization and the right eye sees a different polarization, that results in a stereoscopic or 3D effect. Here's the equation for an electric field of light with polarization in x, y directions. Notice the cosine terms. So I hope you get the idea that trigonometry is useful throughout science and engineering.
Okay, so in the video, you just saw just a small sample of ways in real life that we use trigonometry and the trigonometric ratios. So in today's lesson, we're going to be focusing on just some basic things about right angle trigonometry, and there is a warm-up. So if you would, it'll kind of test your memory on a few topics from geometry. So if you'll pause the video now and complete the warm-up. Okay, so that was probably the easiest warm-up we've had in a very long time. So nice little jog your memory of some things from geometry. In a triangle, if it's a right triangle, you already have a 90-degree angle. So if one of the acute angles is 45, then the other one has to be 45 as well, because your three angles in the triangle have to add up to 180 degrees. if in a right triangle, one of your acute angles is 60 degrees, well then of course the other one would have to be 30 to make that 90 degrees, along with that third angle, which is the right angle, they make 180 degrees. And of course, in example 3 for the warm-up, you had to use Pythagorean's theorem, a squared plus b squared equals c squared, or leg squared plus leg squared equals hypotenuse squared. And when I plugged those in, I ended up finding out that a must be 5. And I just made a little quick note. We're going to want to just consider the positive square root because we're talking about sides of a triangle. Okay, so as I said before, we're going to learn some basics about right angle trigonometry. And so our 2 learning goals are first to understand and use trigonometric relations of acute angles in triangles. And secondly, to determine side lengths of right triangles by using trig functions. Let's start off talking about the domain of these functions, which are called trigonometric functions that we're going to study. So the domain is, in our trigonometric functions, is always represented by the measures of acute angles of a right triangle. And back when we studied trig functions in geometry, we usually used the letter x to represent the angles. But now we're going to use the Greek letter theta. And the theta actually kind of looks like a degree symbol, so that kind of seems appropriate. And our range, when we're talking about our range, those are going to be the things that we get from our functions. These are going to be the trigonometric ratios. And trigonometric ratios always compare side lengths of 2 sides of a right triangle. And you may remember these from geometry, or at least 3 of them. And we used a little mnemonic device, SOHCAHTOA, to remember them. That's the sine, the cosine, and the tangent. So let's do a quick review of these 3 trig ratios. So the sine ratio is represented in a triangle by the ratio that compares the length of the opposite leg to the length of the hypotenuse. So our little mnemonic device, the SOHCAHTOA, the SOH actually represents the sine function. And so in our right triangle, when we talk about comparing the opposite leg to the hypotenuse, we do this in relation to what's called the reference angle. And so, for instance, in this table here, the reference angle is represented by theta, which I just highlighted here. And so the leg opposite would be the side across from that angle. That's the opposite leg. And if I were to compare that to the hypotenuse, which is the leg that's across from the 90-degree angle, that would be this side right here, then that would give me the sine ratio. So comparing those 2 side lengths, how they relate in terms of their lengths, is represented by the sine ratio. And right here is another example of how you can see that sine ratio in a right triangle. So this box over here, we're showing a reference angle. There's the side opposite, and here's the hypotenuse. So when we talk about the words opposite, and we're getting ready to talk about another ratio that uses the phrase adjacent leg. Well, opposite obviously means across from. Adjacent means next to. And when we say opposite and adjacent, sometimes we don't say the whole name of those sides. We actually mean opposite leg and adjacent leg. So that kind of helps with some confusion, because sometimes people get mixed up when we talk about adjacent, which is next to, and the hypotenuse, because you'll see in the triangle that the hypotenuse is always next to the reference angle as well. But we always call that the hypotenuse. So the longest side, the side across from the right angle, is always called the hypotenuse. Oftentimes very helpful to do is to, once you have that reference angle identified, then you label the parts of your right triangle. So the hypotenuse, which is the longest side, that's the side across from the right angle, that's the hypotenuse. The side across from that reference angle, we usually will identify with an O for opposite, and then the leg that's next to it, we label it with an A for adjacent. And so when we go on and we talk about the sine ratio, and we know that the cosine ratio is the ratio of the adjacent leg to the hypotenuse. Looking at my little diagrams over here, this right here shows how to locate the cosine ratio. And in it you just identify your reference angle, and then you compare the adjacent leg to the hypotenuse. And finally we have the tangent, or in our mnemonic device, the TOA part. And the tangent identifies the ratio between the opposite leg and the adjacent leg. So this is the one that compares the two legs. And you can see that in my little box here, right over there. So you may want to jot those down, pause the video and jot those down if you want. If you want an extra diagram that just shows separate triangles identifying each of the ratios. And so again, that's the opposite leg to the reference angle. So in this triangle, the reference angle is angle C. That's the one that they're referencing right there. And so it's the opposite leg over the adjacent leg. So that's comparing the two legs. So when we use this mnemonic device, SOHCAHTOA, the SOH part, SOH means sine is opposite over hypotenuse. And then the ka is the cosine, that's the adjacent over hypotenuse. And then the TOA, that TOA will be the opposite over adjacent. And again, when we say opposite and adjacent, we mean legs. Okay, so I think we've got the ratios down. Let's turn the page. So let's go ahead and test our ability to identify these ratios in an example. It says find the value of the sine, the cosine, and the tangent function for theta. So I can see that they've identified theta as this angle right here in the triangle. So I'm going to use that as my reference angle. So the sine, remember the sine is the SOH. So that means the opposite over the hypotenuse. So if you want to identify these sides in this triangle, the hypotenuse, of course, is the side across from the right angle. The opposite side would be across from the reference angle. This would be O. And then the adjacent leg would be the one that's next to it. So that's A. And so the sine would be the opposite over the hypotenuse, which would be, in this triangle, 7 over 25. Now that fraction can't be reduced, so I'm just going to leave it just like that. And so my sine is 7/25. Now the cosine ratio would be, we know that the cosine is the CAH, so CAH, and that means the cosine is the ratio of the adjacent over the hypotenuse. And so again, in this triangle, it's going to be 24, which is the adjacent leg, over 25. And again, that can't be reduced, so we'll just leave it as 24/25. Now the tangent. The tangent is the TOA, T-O-A, in our SOHCAHTOA. And so that means that's the ratio of the opposite leg over the adjacent leg. And so in this triangle, that's going to be 7 over 24. And again, that cannot be reduced in this case. And so that is my tangent ratio, 7/24. So this is going to be a you try question. I want you to pause the video and give example B a try. And be sure, as you get those ratios, you want to make sure that they are in lowest terms. So reduce your fractions to lowest terms. Pause the video now. All right, so thanks for giving those trig ratios a try. One thing that was a little bit tricky about this triangle, and sometimes, people kind of get so used to the way things are labeled in examples, and so when something like this occurs, it kind of trips them up a little bit. But this time, notice where the reference angle was. It was up here. So we're not always talking about the angle that's formed with, say, a horizontal line or whatever. You just have to look in the triangle, see what angle they're referencing. Sometimes it's labeled with theta, sometimes the vertice will be labeled with a letter. So identify that first, and that's how you reference this opposite and adjacent leg. So in this case, the opposite leg was the leg that was 30, and the adjacent was the one that was 16. And notice I reduced my ratios. So if you, flip-flopped those, then your sine and cosine will be flipped around. So just maybe put a little arrow back and forth if that's what happened, and just remember that next time. Watch real carefully for the reference angle. So obviously there are infinitely many different angle measures. And you can actually calculate the sine and the cosine and the tangent for any angle that's an acute angle, even if it was something like 15.25 degrees. There is a sine, cosine, and a tangent ratio for those. Anything that's an acute angle, we saw that when we talked about the domain. But there are some specific angles within that domain of the acute angles that we consider to be more important than the others. And we call those the special angles. And you may remember some special triangles that we studied back in geometry. And they were the triangles that just kind of occur a lot in everyday life. and they're actually part of some special quadrilaterals that we study, like squares and rectangles and things. And they are the 45-45 right triangle and the 30-60-90 right triangle. And so when you have angles of 30, 45, or 60, we're expected to know the exact sine, cosine, and tangent ratios for those. But they don't turn out to be exact if we just use the calculator to type those in. And we'll talk a little bit more about how to use the calculator to get the trig ratios. But so what we basically do is we just try to commit these to memory. Now we'll talk a little bit later on about some special ways that we can help remember these. But you're just expected to know the special right triangles trig ratios. Now this first triangle here might look familiar to you. It's got a 30-degree angle, a 60-degree angle, and you may remember from back in geometry that there was this special way that the sides related. The smallest side, which is across from the smallest angle, we always called this x. And the hypotenuse was always twice that length, so we always said it was 2x. And then the longest of the legs, which is the side that's across from the 60-degree angle, we always called this the square root of 3x. Okay, so this is really what's going on here. It's just we've dropped the x's off because if all the sides have an x, and we're trying to just find trig ratios, if you were comparing two things that both have an x in them, the x's are going to cancel out anyway. So instead we think of these triangles as having side lengths of 1, which is the smallest side across from 30 degrees, and 2, which is the hypotenuse, and then the longest leg would be just the square root of 3. So we can sort of just get rid of the x's and just focus on these sides. So let's say that I wanted to find the sine, the cosine, and the tangent of 30 degrees. So in this triangle, there's my 30-degree angle. That would be my reference angle. So when I talk about the sine, and the sine is the opposite over the hypotenuse, then the side opposite the 30-degree angle would be the side that was length 1. And then the hypotenuse would be the side that has length 2. So my sine ratio for 30 degrees is 1/2. Well, what about the cosine of 30 degrees? Well, now we want to know the adjacent leg. Well, the adjacent leg is the leg that is square root of 3, and then the hypotenuse is 2. So the cosine of 30 degrees is the square root of 3 over 2. And now the tangent. Well, the side opposite the 30-degree angle is 1, and the side adjacent is the square root of 3. Now, we know that we're not supposed to leave radicals in the denominator, so this would require us to rationalize. So we could just do that by multiplying both the top and the bottom by the square root of 3, and then that would put it in a form that would be considered acceptable. So that turns the top into 1 times the square root of 3, which is the square root of 3. It turns the bottom into the square root of 9, which is 3. And so the tangent of 30 degrees is the square root of 3 over 3. Okay, so what about the sine, cosine, and tangent of 60 degrees? Now, in this case, this is the reference angle over here. So we have to change our perspective in the triangle. Now what sides would have been opposite would now be adjacent and so on. So when I think about the opposite side from 60, this is the opposite leg. The adjacent is the leg that's now 1, so this is the adjacent. And then the hypotenuse is always the hypotenuse. So when I think about the sine of 60 degrees, now I think about going across from the 60-degree angle because it's opposite over hypotenuse. And so that would be the square root of 3 over the hypotenuse, which is 2. And the cosine now of 60 would be taking the adjacent leg. So the adjacent leg is the one that's right next to it. So that's this one, and comparing it to the hypotenuse. And so that's going to be 1 over 2. Now you might notice that if you look at the sine and the cosines of 30 and 60, they're just flip-flopped. And that makes sense because if you're just changing the position in the triangle where you are, which angle is your reference angle, of course that's just going to switch the sine and the cosine because it makes what side was the adjacent now the opposite and vice versa. Now for the tangent, we're going to compare the opposite, which is the square root of 3, to the adjacent, which is 1. And that doesn't have to be rationalized because the radical is on the top. So that just turns out to be the square root of 3 over 1 or just the square root of 3. So one way you can get these trig ratios, other than actually memorizing them, is to use the special right triangles that we learned back in geometry, the 30, 60, 90 triangle, and now when we move on to the 45, 45. But there is a little trick called the finger or the hand trick, and I'll show you that later. Okay, so the 45-45 right triangle. Remember, that's the isosceles right triangle. And so I actually know that this next triangle is an isosceles right triangle because the two legs are equal. And so if the two sides are equal, then it means the two angles across from them are equal, and they both must be equal and add up to 90 degrees, so they have to both be 45 degrees. And you may remember the relationship that existed with this special right triangle. The two legs were called x, and the hypotenuse was called x times the square root of 2. And again, we've just dropped off the x's because when we compare side lengths that both have x in them, the x's are going to cancel out anyway. So now we're just going to think about the triangle as the legs both being 1 and the hypotenuse being just the square root of 2. And so to find the sine of 45 degrees, we can go to actually either one of the angles because they're both 45 degrees. And so if I, say, picked this one to be my 45-degree angle that I'm using as the reference, then I would call this the opposite leg. This would be the adjacent leg. This would be the hypotenuse. And so my sine, SOH, opposite over hypotenuse, would be 1 over the square root of 2. And of course, we have to rationalize that because we can't have a radical on the bottom, so we're going to multiply top and bottom by the square root of 2, and then that leaves me with the square root of 2 over the square root of 4, which is 2. So my sine of 45 degrees is the square root of 2 over 2. And so since the cosine now has the adjacent side that's 1 and the hypotenuse that's the square root of 2, when we rationalize it, it's going to turn out to be the same thing. And so the sine and the cosine of 45 degrees are the same number, square root of 2 over 2. Now finally, the tangent of 45 degrees. So the tangent is going to compare, remember that's TOA, T-O-A, it's going to compare the opposite over the adjacent. Well, the opposite leg is the leg that is 1, and the adjacent leg is 1. So 1 over 1 is 1, and so the tangent of 45 degrees is 1. So that does it for the special right triangles that we need to know the exact sine, cosine, and tangent ratios. So for 30, 60, and 45 degrees, whenever you see those, you need to give these exact values and not maybe values that you would get from the calculator if you were to type in the sine of 45 degrees. We don't want the decimals, we want exact for those values. Okay, let's turn the page. Okay, so now that we know the trig ratios, and we even know some exact trig ratios for some of the special angles, 30, 45, and 60 degrees, now we're going to see how we can take those trig ratios and apply them to find missing parts of some right triangles. So the first examples we're going to look at are in some parts we're looking for in some of these special right triangles. So it says to use a trigonometric function to find the value of x and leave your answer in simplest radical form. Okay, so I have a right triangle here in example A that has a 30-degree angle that is listed. And I know that what that means is this other angle right over here has to be 60 degrees because the angles all have to add up to 180, and we have a 90 and a 30. So this is a 30, 60, 90 right triangle. Now there are different ways that you can find missing parts in the special right triangles. But I want to go ahead and take a look at this as if it were just, just some kind of, not special, kind of triangle, just if it was just a regular, ordinary right triangle, and using the trig ratios. So I erased that 60-degree angle because I want to just have one angle in the triangle to focus on. I want that to be my reference angle. So I'm going to make 30 degrees my reference angle. And so if that were the case, then with my normal way I label the triangle, I would label the side across from it the opposite. I would label the leg adjacent to it adjacent A, and then the hypotenuse I'd label as H. So what I have to do now is decide on a trig ratio that will help me find the missing side that I'm looking for, which is x. So I'm looking to find x. And so I highlighted that. I'm looking to find the opposite. Well, the part that I know is the hypotenuse. So right away I think, what trig ratio uses the opposite and hypotenuse in the ratio? And that's, of course, the sine, SOH. So what I'm going to do is set up this trig ratio and input what I know. So I know that the sine of 30 degrees would have to be equal to the leg opposite, which is x, over the hypotenuse, which is 74. Now I actually know what the sine of 30 degrees is because I remember those exact values. I know that the sine of 30 degrees is 1/2. So if I substitute that in place of sine of 30, then this just becomes a proportion that I can solve using my cross products. So if I use the cross products and multiply across here, I know that 2 times x, which is 2x, must have to equal 1 times 74, which is 74. And now all I have to do to solve is divide by 2. And so then I find out that my x value is half of 74, which is 37. Now you could always think back to when we dealt with the right triangle, special right triangles in geometry, and you think about this triangle with these sides in a certain ratio, and then you could have done this way by just thinking, well, I know the hypotenuse is 74, and the side across from the 30-degree angle is x. Well, if the hypotenuse is 2x and I'm looking for x, I would just have to divide 74 by 2, which is exactly what I did here, or basically multiplied it by a half. Okay, so what about this example with the 45-45 right triangle? And I know that this is one of those isosceles right triangles because it's got a 45-degree angle listed, leaving 45 more degrees for the other acute angle to be. So I start to think about, well, I've got this angle, 45 degrees, and I'm looking for the leg that's opposite it. That's the x, it's labeled that. So that's the O, the opposite. And I have the hypotenuse, which is 20, and then the adjacent leg I don't want or have. So the two that I'm working with are, so since I want the opposite and I have the hypotenuse, I'm going to use the sine ratio again. So I know that the sine of 45 degrees has to be the leg opposite, which in this case is labeled x, divided by the hypotenuse, which is 20. So I know that the sine of 45 degrees, it's one of those special trig ratios that I need to know, and both the sine and the cosine of 45 are both the square root of 2 over 2. So I've got that one kind of in my memory bank, and if not, you'll get to it, to where it'll just come to you. And so I substitute that in for 45, and I know that's got to equal then x over 20, and so now that allows me to just do the cross products now. So I multiply across and across. So 2 times x is supposed to equal 20 times the square root of 2. And so then I can just simply solve by dividing both sides by 2. And I get x equals, well, if I divide 20 by 2, that's 10. That's 10 square root of 2. And so I know that this leg must be 10 times the square root of, which actually means that the leg adjacent is also 10 times the square root of 2. And that's because this is an isosceles right triangle. These sides are congruent. Okay, so how about some real life applications? So in example A, it says in a water skiing competition, a jump ramp has the measurements shown. To the nearest foot, what is the height above the water? So we want the height above the water, h, that a skier leaves the ramp. So they've got that label in our drawing. They want us to find this height right here. And here are the things that we have. We know that this angle right here is 15.1 degrees. That is the measure that the ramp makes with the water. It's a 15.1 degree angle. And I'm looking to find the height, which is, in this case, the leg opposite. And we, again, know the hypotenuse, which is the length of this ramp here. So it's getting a little bit repetitive. We keep having to use the same trig ratio. But again, since we want the opposite and we have the hypotenuse, we have to use the sine ratio. So this time when we write the ratio, we're writing the sine of our reference angle, which is 15.1 degrees, and that is going to be equal to h over 19, where h is that side. Maybe we should have used x or something just because we wouldn't want to get it mixed up with the hypotenuse, but h in this case stands for height. And so if we wanted to solve this, now we don't know the exact trig ratios for sine of 15.1 degrees, and in fact it's not an exact value. It's going to be a number that we would eventually have to round. So this is where our calculator comes in. So the first thing we need to do if we're going to use our calculator for trig ratios is we need to set up our calculator so that it is in degree mode. So on the graphing calculator, we need to hit the mode key, which is up on that first line just below the main keys. And so if we hit the mode key, you'll get to a window that looks like this. And all you got to do is go down to where it's the third line, and you'll see it says radian or degree, and we want to circle degree and press enter. And then you can quick go back out into the window. And that way you've got your calculator set up so that when you type in a number, it with a sine or a cosine or a tangent, it's going to read it as a degree, so it'll know the kind of units that you want because you're setting it as the default. Now the standard way that this comes set up in the calculator is in radians, which we'll talk about later in this chapter, but for now we want to have degrees. So that's the first thing you have to do. So the way that I usually like to approach this is I don't try to find the sine of the or the cosine or tangent or whatever of the angle right away. What I like to do is I think about this as a proportion. So I know I could write the sine of 15.1 degrees over 1, and now I've got a proportion that I can solve using the cross products. So if I multiplied across, I would be multiplying 19 by the sine of 15.1 degrees, and that's going to equal 1 times h, which is h. So now the last thing I have to do to find out what the actual height of this ramp is from the water level is to calculate what 19 times the sine of 15.1 degrees is. And so to do that, I just have to type 19 and then times, and then I'll locate the sine key on my calculator and hit 15.1. And this is what it looks like on your calculator. So on your calculator, you're going to type the 19 in first, and then the times, and then we hit the sine key, which is right here, and then we type in our 15.1 for our degrees, and when we hit enter, it gives us this number, 4.9495856, and so on. And so we have to round, and so we could say that the height is approximately, and they want us to round to the nearest foot. And so rounding to the nearest foot would make it approximately 5. I really prefer rounding to more decimal places, so I probably would have rounded it to maybe hundredths, so I would have said maybe 4.95. So maybe I have to decide about 4.95. But they wanted to the nearest foot, so we gave it to them. Okay, so now that you've seen one of these real-life problems done, what I want to do is leave B as a you try question. And so I want you to take a look at the given information, label the triangle, see if you can figure out which trig ratio, and once you get it set up, use the cross products in your calculator to find the missing link. So pause the video now. All right, so this problem required us to use the cosine ratio. And in fact, a different operation to solve it because we were looking for the hypotenuse. Our variable was located on the denominator of our fraction. And so when I did the cross products, it turned out that over here, I had to, this is what I got from my equation, so I had to divide both sides by the cosine of 17 degrees. And so when I did that and rounded to the nearest inch, as it asked me to do, I got approximately 42 inches. And that answer makes sense. It does need to be the longest side in the triangle because it is the hypotenuse, and it is longer than the 40-inch adjacent side. So 42 inches makes sense. Okay, let's go ahead and turn the page. So you may remember studying angles of elevation and angles of depression in Geometry B. And anytime you have 2 points, for instance, in this drawing here, we have like a person in the airplane and the people that are in the air traffic control tower. And if you were in the plane and you were looking out straight ahead, and you decided to look down at the people in the air traffic tower, you would be looking down from a horizontal, and that's actually called an angle of depression. So looking down is a depression angle from a horizontal. So if instead you were in this air traffic tower and you were looking out horizontal, but then you looked up to look at the plane, and so you turned your eyes upward to look, that angle is an angle of elevation. So whether you have an angle of elevation or you have an angle of depression, it really depends on your position in the situation, your frame of reference. So here's another real-life example that is going to involve depression and elevation angles. So it says a biologist whose eye level is 6 feet above the ground measures the angle of elevation to the top of a tree to be 38.7 degrees. If the biologist is standing 180 feet from the tree's base, what is the height of the tree to the nearest foot? Okay, so here's what this situation looks like. First thing we want to do is draw a diagram. So we're going to draw some, maybe this is my little stick figure. This is the biologist. And his eye level is up here at 6 feet. So he's looking out, if he was looking out straight ahead, and then he looked up, angle of elevation, to the top of this tree, he would be looking up 38.7 degrees. That's what this says right here. 38.7, that's the angle of elevation. So remember that the biologist, we were told, was 180 feet away from a base of a tree. So let's say we had this little tree over here, and of course he was looking up to the top of the tree. So maybe it's a Christmas tree, something like this. And then we've got the stump here. So we've got, and so he's standing 180 feet away from that base. So that means this distance right here is 180 feet. And of course, again, the angle of elevation, which was 37.8 degrees, is right here. And here is the top of the tree up there. So what it creates is basically a triangle. And the tree is part of one of the legs, and the distance away is another one of the legs of the right triangle. And so if we wanted to find out what the height of the tree was to the nearest foot, what we are actually trying to find out is this whole length right here. Now, we can't actually find this whole length of the trig ratio. We can just simply find this piece right here. But we know that the rest of this length from here down is that 6 feet that his eye level was at. So this was 6 feet. So what we're going to want to do is find this length that maybe we'll call x here, and then circle it. We're going to try to find x, and then what we'll have to do is add 6 at the end. So we'll have to add the height of the person's eye level in at the end. So when I take a look at the parts that I'm given and I want, so I'm given this part of my right triangle and I want this part. Well, those are both legs, so I know that that has to be the tangent ratio. So I'm going to write the tangent of 38.7 degrees is going to be equal to the opposite, which in this case is x, and the adjacent, which is 180 feet. So if I just go ahead and put the tangent of 38.7 degrees over 1, and I can solve this using my cross products, just like the last problem. So I do the cross products. I'm going to be multiplying 180 by the tangent of 38.7 degrees, and that's going to equal x. And let me check my calculator. So x turns out to be about 144.20719 and so on. But it says they want me to round to the nearest foot, so I'm going to round to 144 feet. Well, that's not how tall the tree is, because remember we have to add this part in here, the 6. So it's really 144 plus 6 feet for a total of 150 feet tall. So I don't know much about trees, but I think that's a pretty tall tree. So here's yet another way that we can use trigonometry to solve real-life problems. Our final thing we're going to be looking at are some new trig ratios. We're pretty familiar with the common sine, cosine, and tangent ratios. Well, it turns out that there are actually 3 other trig ratios, but they are related to the ones that we know. Now, the first one is the cosecant, and it actually is abbreviated as CSC, so the cosecant of an angle. And it turns out that the cosecant is the reciprocal of the sine function. And so we know that the sine function is actually the opposite. So we know sine is opposite over hypotenuse. So that means that the cosecant, if it's the reciprocal of that, would actually have to be the hypotenuse over the opposite. So the reciprocal of the sine, or 1 over the sine, would be the hypotenuse over the opposite leg. So the reciprocal of the sine. The cosecant is actually the reciprocal of the cosine, and so that's actually abbreviated as SEC. And the 1 over the cosine would be the same as the secant. So I know that the cosine, remember the cosine is ca, C-A-H, so that's adjacent over hypotenuse. So then the secant would be hypotenuse over adjacent. And finally the cotangent. And the cotangent is actually the reciprocal of the tangent. And so we could write it as 1 over the tangent. But because the tangent is the opposite over adjacent, or TOA, then if we took the reciprocal of that, we flipped it, it would actually be the adjacent over the opposite. So these are, less often used, but still are important. And so, it's important to kind of look at how we can calculate those. But really, our main focus is still going to be on the 3 big ones, the sine, cosine, and the tangent. But this last and final example is going to be looking at how we can calculate these additional 3 trig ratios in some given triangles. So let's turn the page and take a look at that. Now I haven't ever heard of a really good mnemonic device to remember those. Really the easiest way to remember them is to know that the cosecant is the reciprocal of the sine. And so if you know the sine for so, just flip the O and the H around. And the same thing with the secant and the cotangent. So I have this triangle here, and if I ask you to find all these 6 trigonometric ratios for the reference angle theta, well, in order to find all these 6 ratios, I actually need to know all the sides. Because notice in this triangle, I don't even know the hypotenuse, which would basically leave out the sine, the cosine, and now the reciprocals of those, the cosecant and the secant. I would only be able to find the tangent and the cotangent ratio. But we know that in a right triangle, we can always use Pythagorean's theorem to find any missing parts if we know the other 2. And so that's the first thing we need to do here is figure out what the third side is, and then we can find all these trig ratios pretty easily. So if I were to plug these 2 legs in, I know the 2 legs, A and the B, and if I plug those into Pythagorean's theorem, I have 70 squared plus 24 squared, which is 5,476 when I square them and add them together, and that's equal to c squared. So if I want to know what c is, I just simply have to take the square root, and that turns out to be 74. So I know that my hypotenuse is 74. And so now I can calculate all my trig ratios. And since these are all even numbers, I'm going to have to reduce them. So let's see the sine. So the sine of theta would be the opposite, which is 70 over 74. And we can reduce that to 35/37. Now before I go on and do the cosine, which I'm kind of in, that mode where I usually go the sine, then cosine, but remember the cosecant is the reciprocal of the sine. So I can get this ratio just by flipping the one that I have. So the sine, if I flip that, I get 37 over 35. So now I've got the cosecant taken care of. So the cosine is going to be the adjacent leg, which is 24. And compare it to the hypotenuse, which we found to be 74, and that reduces to 12/37, which means that if I flip that to get the secant, that's going to be 37/12. And finally, the tangent is the opposite leg, which is the 70 in this case, compared to the adjacent leg, which is the 24. And that reduces down to 35/12. And then the cotangent, we can just flip that, and that gives us 12/35. So let's see if we have the hang of this, and let's set B to be the you try question. So go ahead and pause the video now. So pause the video now and find the hypotenuse, and then calculate the 6 trig ratios. Okay, so how did you do? Always make sure that you reduce these to lowest terms, and once you do that and you calculate your 3 big ones, the sine, cosine, and the tangent, it's really very easy to get the cosecant, the secant, and the cotangent. So that's our final example, and that's going to do it for today's lesson. So I will see you in class.